Muhammad Alif bin Muhammad Ali. My name is Muhammad Sirhan bin Muhammad Siraj.
My name is Faris Akmal bin Muhammad Ghazali.
My name is Muhammad Hafiq bin Muhammad Nudin.
My name is Muhammad Syafiq Abdul Malik.
My name is Nur Fadilah binti Wan Musa.
My name is Wan Muhammad Syamil bin Wan Musa.
My name is Muhammad Syarul Izani bin Syafarid.
My name is Nur Aini binti Muhammad.
When we hear the word radiation, it's tempting to picture huge explosions and frightening mutations. But that's not the full story. Radiation also applies to rainbows and a doctor examining an X-ray. So what is radiation really, and how much should we worry about its effects? The answer begins with understanding that the word radiation describes two very different scientific phenomena: electromagnetic radiation and nuclear radiation. Electromagnetic radiation is pure energy consisting of interacting electrical and magnetic waves oscillating through space. As these waves oscillate faster, they scale up in energy. At the lower end of the spectrum, there's radio, infrared, and visible light. At the higher end are ultraviolet, X-ray, and gamma rays. Modern society is shaped by sending and detecting electromagnetic radiation. We might download an email to our phone via radio waves to open an image of an X-ray print, which we can see because our screen emits visible light. Nuclear radiation, on the other hand, originates in the atomic nucleus, where protons repel each other due to their mutually positive charges. A phenomenon known as the strong nuclear force struggles to overcome this repulsion and keep the nucleus intact. However, some combinations of protons and neutrons, known as isotopes, remain unstable or radioactive. They will randomly eject matter and/or energy known as nuclear radiation to achieve greater stability. Nuclear radiation comes from natural sources like radon, a gas which seeps up from the ground. We also refine naturally occurring radioactive ores to fuel nuclear power plants. Even bananas contain trace amounts of a radioactive potassium isotope. So if we live in a world of radiation, how can we escape its dangerous effects? To start, not all radiation is hazardous. Radiation becomes risky when it rips atoms' electrons away upon impact, a process that can damage DNA. This is known as ionizing radiation, because an atom that has lost or gained electrons is called an ion. All nuclear radiation is ionizing, while only the highest energy electromagnetic radiation is. That includes gamma rays, X-rays, and the high energy end of ultraviolet. That's why, as an extra precaution during X-rays, doctors shield body parts they don't need to examine, and why beachgoers use sunscreen. In comparison, cell phones and microwaves operate at the lower end of the spectrum, so there is no risk of ionizing radiation from their use. The biggest health risk occurs when lots of ionizing radiation hits us in a short time period, also known as an acute exposure. Acute exposures overwhelm the body's natural ability to repair the damage. This can trigger cancers, cellular dysfunction, and potentially even death. Fortunately, acute exposures are rare, but we are exposed daily to lower levels of ionizing radiation from both natural and man-made sources. Scientists have a harder time quantifying these risks. Your body often repairs damage from small amounts of ionizing radiation, and if it can't, the results of damage may not manifest for a decade or more. One way scientists compare ionizing radiation exposure is a unit called the sievert. An acute exposure to 1 sievert will probably cause nausea within hours, and 4 sieverts could be fatal. However, our normal daily exposures are far lower. The average person receives 6.2 millisieverts of radiation from all sources annually, around a third due to radon. At only 5 microsieverts each, you'd need to get more than 1,200 dental X-rays to rack up your annual dosage. And remember that banana? If you could absorb all the banana's radiation, you'd need around 170 a day to hit your annual dosage. We live in a world of radiation. However, much of that radiation is non-ionizing. For the remainder that is ionizing, our exposures are usually low, and choices like getting your home tested for radon and wearing sunscreen can help reduce the associated health risks. Marie Curie, one of the early radiation pioneers, summed up the challenge as follows. Nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less.
What is heat radiation? Heat can be received in any means of transfer. As we experience normally in daily life, heat transfer usually by conduction and convection. If you imagine a scenery, you and friends sightseeing in sunny day at London, you feel hot as heat transfer from the sun. But how does the sun that is 100 miles away from us can transfer heat? The space between sun and earth is called vacuum, and it has no particles that can transfer heat by conduction and convection. So how does the sun transfer heat to us? Well, the sun transfers heat by using infrared or infrared radiation. This is usually called as heat radiation. Heat radiation, as opposed to particle radiation, is the transfer of internal energy in the form of electromagnetic wave. For most bodies on Earth, this radiation lies in the infrared region of the electromagnetic spectrum. One of the first to recognize that heat radiation is related to light was the English astronomer William Herschel, who noticed in 1800 that if a thermometer was moved from one end of a prism-produced spectrum to the other, the highest temperature would register below the red band, where no light was visible. Because of this position, this form of radiation is called infrared, or infrared being the Latin word for below or within. Sometimes, this kind of radiation is called a heat wave, but this is a misnomer. Recall that heat is the transfer of internal energy from one region to another, as all forms of electromagnetic radiation transfer internal energy that could all be called heat wave.
Radiation differs from conduction and convection heat transfer mechanism in the sense that it does not require the presence of a material medium to occur. Energy transfer by radiation occurs at the speed of light and suffers no attenuation in vacuum. Radiation can occur between two bodies separated by a medium colder than both bodies. According to Maxwell theory, energy transfer takes place via electromagnetic wave in radiation. Electromagnetic wave transport energy like other waves and travel at the speed of light. Electromagnetic waves are characterized by this formula, where V is the frequency with the unit of hertz, and lambda for the wavelength with the unit of micrometer, and C here is the speed of light in that medium. In a vacuum, where C0 is equal to 2.99 times 10 to the power of 8 meter per second. Note that the frequency and wavelength are inversely proportional.
Hi everyone! Today, I'm going to present about the properties of radiation. Basically, there are 4 types of radiation which emits off by radioactive atom, which are, first one is alpha, followed by gamma, beta and neutron particles. And I'm only going to explain about the 3 out of the 4, which is the alpha, beta and gamma particles. Radioactive atoms give off one or more of this type of radiation to reach a more stable state. The word properties mean how they behave, and right now we are going to focus on 3 properties, which is the first is their range in the air, and in other words how far they can travel in air before they stop. And the second property is their penetrating power, which means what type of radiation can pass through. And the third property is their ionizing power, which sounds tricky but not as difficult as it sounds. Okay, some elements are radioactive, and that means that That means that they decay and release radiation from the nucleus. Always remember that this is a totally random process and we absolutely cannot predict when any individual atom will decay. Scientists cannot do anything to make decay faster or slower. Next, we are going to look at 3 different types of radiation, which are called alpha, beta and gamma. Alpha particles consist of 2 protons joined to 2 neutrons. In other words, this is the same as the nucleus of a helium atom. That means that an alpha particle is quite large. Beta particles are electrons produced in the nucleus which then fly out, which is very small. And the last one is gamma radiation. Is a very high energy electromagnetic wave. Gamma radiation has got no mass. So let's start taking a look at their range. In air, alpha particles are quite big, so they can travel to a run of 5 cm air before colliding with an air particle and stop. Beta particles are much smaller, so they can travel around 20 cm in air before they collide with air particles and stop. And gamma radiation is a very high energy electromagnetic wave, so it can travel through several meters of air before it stops. So, to summarize, alpha radiation is stopped by a few centimeters of air. Beta radiation is stopped by around 20 centimeters of air, and gamma radiation has stopped by several meters of air. Okay, so now we are going to take a look at the penetrating power of each radiation. This means each radiation can pass through. Alpha particles can be stopped by a single sheet of paper, so they are very easy to stop, while beta particles are a bit harder to stop. They need a few millimeters of aluminium to stop the particles. Gamma radiation is extremely hard to stop, so to do that, we need several centimeters of lead. Okay, next, let's take a look at the ionizing power of each type of radiation. So, what does that mean? Well, the key fact is that when radiation collides with atoms, this can cause the atoms to lose or gain electrons. We call an atom which has lost or gained electron as an ion. Alpha particles are very strongly ionizing, which means that alpha particles can create a lot of ions. Beta particles are quite strongly ionizing, so they create a quite large amount of ions, but not as many as alpha particles. Gamma radiation is weakly ionizing, so it does not create a lot of ions. Okay guys, so hopefully now you guys can describe the properties of alpha, beta and gamma radiation. This is include their range in air, their penetrating power and the ionizing power.
Okay, I'll be explaining about blackbody concept. In engineering, we approach a certain concept with an ideal perception, a concept without restraint or setbacks, and then later breaking down these flawless layers by implementing limitations. For example, an acceleration without friction and the flow of electricity without resistance. The blackbody concept is one of the many perfect concepts out there, but focus on heat absorption. The idea of perfect heat absorption, the blackbody concept is essential when studying the absorption of wavelength, especially but not limited to thermal and electromagnetic radiation. This means that anything, absolutely anything, that comes in the form of wavelength or radiation is completely absorbed by that body. This concept is used as a benchmark or standard and compared with real-life phenomena. Why blackbody? Because those bodies that absorb incident with visible light will seem black to the human eyes. For example, we can hardly characterize our sun, which is indeed almost a black body within a very wide band of electromagnetic radiation wavelength as a physical object in optics. It is namely bright white sunlight, which represents the equilibrium black body radiation. One of the many applications of the black body is an optical band. Familiar of bandwidth? It is the transfer of data through wavelength. Optical band utilize light as the source of wavelengths to pass on data. The body concept is the black body concept is applied in the cable or the medium for the transfer of this wavelength. Unify, as we know, implements these ideas. Some of the material are known as soot, silicon carbide platinum, and golden nylon. Another application is one that occurs naturally. All of the planets in our solar system, even Sun, has the characteristics of a black body. Rough surface allow it to absorb radiation while also having the ability to emit its own radiance through emissivity.
Next, I would like to explain the black body radiation known as cavity radiations, the electromagnetic radiation that will be radiated from an ideal black body. Where are the black body radiations comes from? The sources of black body radiation consist of three, which are cosmic microwave background (CMB), the Sun and the Earth. Cosmic microwave background is one of the universe fluctuations magnetic radiations that fills the part of the universe. The radiation possesses nearly isotropic spatial angular field with an intensity that can be characterized by the radial brightness temperature of 2.73 Kelvin. Next, to determine the accuracy, directions, and velocity of the motions of the solar system. Next, the Sun. The presence of thermal black body radiations with a brightness temperature of 5,800 Kelvin at the Sun. Along with black body radiations, there exists powerful, non-stationary quasi-noise radiations, such as flares and storms. Next, the Earth possesses radiations close to the black body radiation with thermodynamic temperature of 287 Kelvin. In the black body radiations, there consists of laws, which are Stefan's law and displacement law. Stefan's law: the energy radiated by a black body radiator per second per unit area is proportional to the power of the absolute temperature. Next, for the Wick's displacement law 1893, the wavelength distribution is fixed at the value that is inversely proportional to the temperature.
Hello everyone, I'm going to talk about the factor in radiation transfer for various geometries. In heat exchange between two or more surfaces which has practical importance to the surface which are not in direct contact, exchange the heat due to the radiation. The factor thus determine the rate of heat exchange between two surfaces or bodies are the temperature of the individual surface, their density, as well as how well one surface can see another surface. The last factor is known as beam factor or shape factor. Shape factor is defined as a fraction of energy emitted by one surface and directly intercepted by another surface. The value of the shape factor depends only on the geometrical configuration of the system. Is also known as the geometrical factor or configuration factor. The radiation shape factor for surface 1 and 2 is given as a shape factor of the area 1 with respect to area 2 equal to the ratio of direct radiation from surface 1 incident on surface 2 to total radiation emitted from surface 1. F12 equal to the fraction of the energy leaving one which reach surface 2. F21 equal to fraction the energy leaving surface 2 which reaches surface 1. Or in general, Fm and equal to fraction of the energy leaving surface M which reaches surface in energy leaving surface 1 and deriving at the space to the energy leaving surface 2 and arriving at the surface 1 given us. All the incident radiation will absorb by the black body at the net energy exchange will at the thermal equilibrium between the surface. Equation A1 F12 equal to A2 F21 is known as reciprocating relation and it can be applied in general way to any black body surface and Fm and equal to a Fnm. Shape factor surface with respect to itself is the fraction of energy emitted by the surface which is intersection by surface itself. Shape factor is the respect to itself for convex surface and plane surface is always 0. When the area receiving the radiation is divided into a number of substance area, then a submission theorem can be applied. Let us consider radiation area A1 and receiving A2 which is divided into area A3 and A4. Applying summation theorem can begin.
Now I will explain about relationship. Relationship is a radiation heat transfer between two surfaces can be reduced greatly by inserting a thin high reflectivity sheet of material between the two surfaces. Such highly reflective plates or shell are called relationship. Multi-layer radiation sheets are consisted of about 20 sheets per centimeter thickness. Separated by evacuated space are commonly used in serogenic and space application. Radiation sheets are also used in temperature measurement of fluids to reduce the error caused by the radiation effect when the temperature sensor is exposed to the surface that are much hotter or colder than the fluid itself. The role of the radiation sheet is to reduce the rate of radiation heat transfer by placing additional resistance in the path of radiation heat flow. Theoretically, the lower emissivity of the shield, the higher the resistance. Note that the emissivity of different surface of the shield may be different.
In chemical industry, it is noted that heat is lost through the surrounding and through the radiation. So, we should use the application of radiation sheet to minimize this effect. Radiation sheet is placed in front of the equipment to reduce the loss of the heat from radiation to the surrounding. The radiation sheet are also used to prevent the equipment from damage. This is because the material used for radiation has low emissivity and high reflectivity. One of the application of the radiation shield is used in spacecraft. It is used for protection against thermal radiation that can potentially damage the equipment involved. The multi-layer construction prevents radiation heat being transmitted both by radiation and convection.
June.
Assalamualaikum warahmatullahi wabarakatuh. My name is Tristan. So before we get to the conclusion, I want to break down and summarize all of the main factors which are radiation heat transfer, a black body concept, and radiation shield. So in radiation heat transfer, there are three heat energy is carried by the movement of particles of matter. For example, when there is a fire beside me, I would feel heat and or temperature that is come from fire. So, in conduction, heat is transferred by particles vibrating. So, for example, heating metal rod. So, in radiation, heat is carried directly by electromagnetic waves such as radiation heat in the sun. When a hot object touches a cool object, the heat moves from the hot one to the cool one. When objects transfer heat, they cool down to a lower temperature unless the heat energy they lose is constantly replaced. As for the black body concept, a black body is one that absorbs all incoming light and does not reflect any. At room temperature, such as an object would appear to be perfectly black. However, if heated to a high temperature, a black body will begin to glow with thermal radiation. For example, an iron bar becomes orange red when heated to a high temperature, and its color progressively shifts towards blue and white as it is heated further. It is also known as cavity radiation because black body is a cavity with a small hole in it. Any light incident upon the hole goes into the cavity and is essentially never reflected out, since it would have to undergo a very large number of reflections of walls of the cavity. So if we make the walls absorptive, so maybe such as paint the walls black, the cavity makes a perfect black body. So, as for the radiation shield is a protection against thermal radiation that can damage the inside of the object, in which the radiation shield are commonly used in spacecraft such as airplane or helicopter or rocket ship, because the temperature at higher altitude is very high. So, as for this knowledge of radiation is very important to our life, because if we know about this, we could prevent dangerous causes such as radiation, heat exhaustion, which can lead to heat stroke and cancer, and any other form that can caused by